These are the AP Physics 1 vector and scalar notes. They go along with our trig information for our vector and trig exam. Let's talk about the basic definitions real quick of scalar and vector. Now I will remind you, you do have a note packet where you can write this information down. On the back of the front page, it says scalar versus vector, and this is where this information can be written. So scalar actually is any quantity in physics that has magnitude. Well, what's magnitude? Magnitude is a numerical value with units, but scalar values don't have any direction associated with them. Okay, so some examples would be things like speed, just a magnitude. Distance, just a magnitude. Age, just a magnitude. And heat, just a magnitude. So again, a magnitude is just a numerical value with units. It doesn't have any direction associated with it. I'll also remind you, scalar and vector are some of your vocabulary words that you need to know from the front of the packet as well. A vector, on the other hand, is any quantity in physics that has both magnitude and direction. So if you look at your formula chart, there are some things that are listed. So I want you to pull those out. Make sure you have those out as well right now. So a vector quantity would be something like velocity, 20 meters per second, and directional, north. Okay, or acceleration, which is 10 meters per second, or 10 meters per second squared, east. And force, which is something we'll talk a lot about this semester and this year, and that would be like 5 newtons west. Now on your formula chart, vectors are going to be illustrated by drawing an arrow above the symbol. It's used to convey direction and magnitude. So I want you to take just a few minutes and look at your formula chart and see how many things have arrows over them. All right? So this would be where you could pause and check that out real quick. Everybody take a minute to do that. Now as we move over into our note information, we have some that are going to be graphical and we have some that are going to be mathematical. Right now we're going to talk only about the mathematical ones. So some of them I will be skipping over. So for example, this one actually is example 1, but I want you to actually skip past it. Okay? So, oops, we're going to go back. So when I am doing vector addition, okay, mathematically, this would be if I have 2 similar vectors that point in the same direction, then I'm going to add them together. Okay, vectors are really just arrows or directional pieces. So again, if I draw those lines and they're both pointing in the same direction, then I'm going to add them together. So going to example 2 is where I want you to be right now in your note packet. A man walks 54.5 meters east and then another 30 meters east. Calculate his displacement, which is a vector value, relative to where he started. So displacement is the distance and direction put together. So we draw our line that's going to what I would consider be east on my paper. And that I'm going to label it as 54.5 meters. I don't have to put the east there because the arrow actually shows me east. But then I'm going to do another arrow. And this is how we draw vectors. We draw them from tip to tail. So when you do that, what I'm talking about here is, and these wouldn't have to be a scale, but I do sketch this type of problem out on my paper. I think it's important. So notice I did the first arrow in blue, and then at the tip of the blue arrow, I put the red arrow's tail. That's how I would draw tip to tail. So that's the method of how we draw vectors. Okay? Then I would label this one 30 meters east. I'm not concerned about their size, except notice I did put the blue one bigger than the red one, and that's because 54.5 meters is bigger than 30. So we can make sure that our representations match there. Now if I want to find displacement, and these are in the same directions, then I'm going to go from where I started all the way to where I ended. And so that would be added together 84.5 meters east. So my answer would be 84.5 meters east, because I have to have not only the magnitude, but also the direction. So notice that the size of the arrow conveys my magnitude. It's bigger. My purple one is bigger than both of my individuals. And it is drawn to show my direction as well. So skipping past our graphical subtraction. Okay, I now want to do my mathematical subtraction. If you have two vectors that are in opposite directions, you will subtract them. Okay, so now I have a man that's walking 54 meters east and then 30 meters west. Actually, this might be example 2 instead. Actually, it is. I think it's, yeah. Okay. And so the other one we could have done on is example 1. Let me go back. No, it won't matter. You'll already have done it. So it doesn't matter. They're the same numbers anyway, so you can do it on either one of these. But you just need to pay attention to his actual direction. So if you did the previous problem in number 2, draw an arrow and put it up in number 1, and then you can draw it an arrow down and switch it. I'm sorry about that, guys. My bad. So a man walks 54.5 meters east and then 30 meters west. Calculate his displacement relative to where he started. Again, sketch them. So we have 54.5 meters east, and then we have 30 meters west, which now resultant-wise, I'm going from where he started to where he finished. Okay, and again, we do them tip to tail. So notice the blue one, I started the red one at the tip of the blue one and went backwards. And now for the resultant, which is my purple one, I always start with its tail where I originally started, and then I run it up to the where I finished. So that's the only time the tails are together and the tip is together, is when you have the resultant. So when I do that subtraction, I end up with 24.5 meters east, because I was going more east than I was going west. So that tells me both the magnitude and the direction. Okay, when I have non-collinear vectors, this one's talking about them graphically, but so I'm going to skip past it real quick. I think I can do it actually. No, let's go back. All right. So this one talks about it graphically, but really whether you're doing it graphically or whether you're doing it mathematically, you do it the same way. So the non-collinear ones is going to be where we have vectors that are going to move perpendicular to each other instead of moving on the same plane. So on our first two examples, we're only moving east and west. So those were linear. We could also say we only move north and south. Those would be linear. But now, since we're going to move north, and then we're going to move south, and then we might move east, and then we will move west, and then we might move south again, and then we might move west again. So, I mean, we're not always going to stay in the same plane. That's what we mean by non-collinear vectors, okay? So, again, we're going to have to use the tip-to-tail method, which I already brought up. And when we do this, we're going to always draw them so that we create right angles, okay, if we can. So I have, this is my example 3, I think. Yes, it is. Okay, so I have that he's going to walk 95 kilometers east. So I'm going to draw that 95 kilometers east and label it. And I put my arrow tip on it. So now I'm going to do my tip to tail method, but I'm going to go 55 kilometers north. So I'm going to draw this one going north. And again, I did from the tip of my first one is where I put my tail of my second, and I finished with that vector. So now to find the resultant, I'm going to start at my origin, and I'm going to finish at my tip of my last vector. So I'm going to draw a line from my original tail to my final tip. Okay, that is now actually known as my resultant. Okay, so this hypotenuse in physics is going to be called the resultant. We always call that hypotenuse the resultant, by the way. Okay, so then the legs of the triangle are known as our sides of our triangle, and they are our adjacent and opposite sides and things like that. But we call those our components. So our 95 kilometers east would be our x component, and our 55 kilometers north would be our y component. Okay, we could also talk about them as the horizontal component and the vertical component. All right, so we can go back to that if you need to, or we can pause it so you guys can get those drawings. So in our previous example, our displacement was asked for, and since it's a vector, we should include the direction in our final answer as well. So note when we're drawing a right triangle that conveys some sort of motion, we have to draw our components tip to tail, which we already talked about. Okay, and we have our 90-degree angle here. So now what we have to think about is we have to think about how do we talk about where we started to where we finished directionally. Okay, so we kind of think about a compass rose, and I do recommend that you draw this on the bottom right corner of this back front page. Okay, so when we were calculating it, if I go back a slide real quickly, I could figure out the value of this sloped line, but I'm going to get there in a minute, so I want to talk about its direction first, because finding that value is super easy, and so we'll be able to do that. So when I talk about the directional information, I can either talk about it in bearings or I can talk about it with directional information like the compass rose. So I always start with my north at the top and then my east and my south and my west. All right. Now, we know these as quadrants as well. So quadrant 1 is over here, and we have quadrant 2 over here, quadrant 3 down here. Oops, that did not look like a 3, guys. Sorry. And then we have quadrant 4 over here in the corner. Now, each one of these quadrants has 2 separate angles that we could talk about. So, if I have this line, very similar to my example problem here, in quadrant 1, I can label it 2 different ways. If I talk about the angle that comes up from the east, just like that, then I'm going to name that north of east, and I recommend you write this on your paper, okay? Whereas if I talk about this angle instead, coming off the north and going there, then that's going to be labeled east of north. So that would be for quadrant 1. We have 2 separate angles depending on where we measured from, or where we started from. Then if I go into quadrant 3, I again have 2 separate angles, so I could measure from here, or I could measure from here. If I measure from where I put the black line, that would be my south of west, because I go from my west line, I go south. So really I can go out my west line and then I went south from it. Okay, that's why I name it like that. And then if I went from my red line, here, my red angle, so I start from the south and I move to the west. So that would be called my west of south. So it's always about where you're measuring from. It goes last. And then you tell which direction you're going from that, which way you go from that. So on this one, if I went up from the west, that would be my north of west. Or if I came this direction from the north, then that would be west of north. And if I went down in quadrant 4 here, then I would say it was south of east if I go here, and it would be east of south if I go here. Okay, so that's a way to think about how you write these. Another way to think about it is it's always the opposite of adjacent if you're talking about directional information. Okay, that's another way to remember it. Whatever direction the opposite side is going of whatever the adjacent side is going, because that's in accordance to your angle. So that is another way of thinking about it. All right, so this one would be north of east because we're measuring our angle up from the east, and we go above it, so that's north of east. Okay, so back to my problem. Just saying north of east, though, is not specific enough. We actually have to find the value of the angle. To do that, we would use trig. Okay, so we find that theta, and we would go ahead and say that we have our, we could do our inverse tangent. So our theta would be found by doing inverse tangent opposite of adjacent. Okay? So I think on my next couple of slides I actually do that. So I have my two vectors. Here's the same problem. I have my 95 kilometers east. I have my 55 kilometers north. I've drawn them tip to tail. I start there. I finish there. I draw my resultant from where I started to where I finished. And now I'm going to actually solve for the resultant by using Pythagorean theorem. Okay, so when I do that, I would do my a squared plus b squared equals c squared. I'm trying to find c, so I would take my 95, square it, plus 55, square it, and then take the square root. I'm pretty sure that my answer is not rounded properly. It's not. It should be, go ahead and do it in your calculator, and you'll see that it should have two numbers after the decimal, not just one, and you guys need to talk about what those two decimals should be as a class. Make sure everybody's on the same page with what those should be. Okay, do it in your calculator. Don't ever take my word that these are right, because again, I'm not perfect, and I'm more than willing to make sure that you guys are doing it right and double checking me. All right? So that's not all of it, though. That's just the magnitude. So now we need to find, see, and I wrote it right here. Okay, now we need to find the actual angle value. So we would use our inverse tangent. We would do 55 kilometers over 95 kilometers. I did not show my units in my work here, so that's not good. Remember to do that. And then that would be a 30-degree angle. So my complete answer would be 109.77 kilometers and 30 point, again, I didn't show my decimals, 0.07 degrees north of east. All right, so that's how we do these types of problems using trig and Pythagorean theorem. I'm going to skip that one, and you're going to turn the page in your notes. And I think example 4 is just a continuation of example 3. So just FYI, that's a little bit more space for you to work part of it if you needed it or to go back and look at it again. So suppose a person is walking 65 meters and 25 degrees north or east of north. What's his horizontal and vertical component? Okay, so here on this one, we're on example number 5 in your packet. Okay, I'm going to go ahead and draw my compass rose, and I'm going to say that north is up and east is to the right, and then south is down and west is to the left. So my arrow would look a little bit like this. I should have made a better right angle here. Let me see if I can fix it real quick. It's magical. Here. Doom, doom, doom. Now it's fixed. All right, so now I'm in the corner there of that, and I don't know why exactly I have a dot, but that's good. So to solve for components, we're going to use trig functions like sine and cosine. So in order to go this, I went 65 meters, and I'm at an angle of 20 degrees east of north, which means I started on the north, and I went east, and that's my 25 degrees. Okay? So I want to be able to go up, and then I'm going to go over. So I have to find my vertical component or my y component, and then my horizontal component or my x component. So to find the horizontal component, my horizontal component would be my opposite side, because this is my opposite side. And my vertical component would be my adjacent side. So I would use cosine to find my vertical component, and I would use sine to find my horizontal component. These should be correct, and notice I gave the displacements on my components to be not only the value, the magnitude, but also the direction that I had to go. double check my math because I didn't show all my work here, but double check that as you go along. Now I've got my bear that's going to search for food, and I really like to do this one actually as a graphical and as a mathematical, but I guess we'll go ahead and just, I want to hold off and do it graphically. So we're going to do this one, even though it says calculate, we're going to do it graphically later on. So I want you to skip example 6 for now, and we'll come back to it. Okay? I probably ought to just pop. So let's move on to number 7. A boat moves with a velocity of 15 meters per second north in a river which flows with a velocity of 8 meters per second west. Calculate the resultant velocity of the boat with respect to due north. So again, we're going to draw it. I always recommend doing your compass rose and drawing it. So we go 15 meters per second north. The current is going to push us to the west at 8 meters per second. And so I want to find the resultant. Okay. Now I want to find that RV, so I'll say it's the resultant velocity. Lots of times instead of saying RV, I'll do V sub R. So that will be the same thing as my velocity, but it's the resultant velocity. And I want to find my angle down here. Okay, most of the time we do find our angle closest to where we started. So when we look at our triangles, we try to do that. So I would do Pythagorean theorem, and I would have my 8 squared plus 15 squared, and again, I did not include my units, so that's bad. And then I take the square root, which would give me 17 meters per second. And then I would take my inverse tangent of my opposite over my adjacent, which would be my 8 meters per second over my 15 meters per second. And then I would get my degrees. So I would end up with a final answer of 17 meters per second at a 28.07 degrees west of north. I highly recommend you pausing the video and doing these problems and checking to make sure you can get the same answers in your notes. All right, so now we're on a plane, and it moves with a velocity of 63.5 meters per second at 32 degrees south of east. So again, draw your compass rose. East is the last direction, so we're measuring from the east. So we're going to go into quadrant 4. So we're going to draw our information here. This time again, I want to find my horizontal and my vertical components. So I want to find horizontal component here because I got to go to the east first, and then I'm going to go south. And remember I said it was opposite of adjacent. So this was my opposite side, and this was my adjacent side. That's the other way of talking about this. And now I want you to pause the video and solve for the horizontal and vertical components and see if you can come up with them. Now lots of times I'm going to list these as Vx and Vy, okay, because they gave me my resultant value. So this would be my Vr. So that might be some of the ways that I denote this stuff as well when we work problems. So again, pause the video now and work this problem. When we use our sine and cosine, y'all should have gotten answers of 53.85 meters per second east and 33.64 meters per second south. Again, you have to give magnitude and direction. All right. So in my next one, a storm system moves 5,000 kilometers due east and then shifts course at 40 degrees north of east for 1,500 kilometers. Calculate the storm's resultant displacement. Okay. Now, this one I start off with 5,000 kilometers east. Now on this next one, I was told to go an angle for my next part. So I have to do this tip to tail. So at the very tip of this one that I just drew going east, I'm going to draw a compass rose. Okay, because now I'm going to have to do an angle from this location. So I'm going to do 40 degrees north of east. So I'm going to measure up into quadrant 1 from my compass rose, and I'm going to go 1,500 kilometers. So it's going to be like that. Okay, so then when I take away my compass rose, I look like this right now. And I have an angle drawn here of 40 degrees up like this. Okay, well, I want to calculate the resultant displacement. Well, hold on a second. Let me go back for a minute. My resultant displacement is actually from here where I started. Oh, that is not a pretty line. To there where I finished. Well, remember when I told you we were going to have right angles only? And we were going to have right triangles? Well, that's not a right triangle. So what I'm going to have to do is I'm going to have to extend some pieces here. And I'm going to have to create a horizontal component here and a vertical component here. Now, if I do the 5,000 plus my horizontal component, I will have a new x component and I will have a y component. And I can use this little bitty triangle that has the 1,500 kilometers as the hypotenuse and my angle of 40 to find my x and y components over here. Okay, so if I do that, I can then find that this extra little piece, my x component, which I'm going to say x equals and y equals, would be my 1,149.1, and my opposite, my y component, would be my 964.2. So really now my entire x piece is the 5,000 plus the 1,149. So I end up with an entire x piece that is 6,149.1. So that's my new x component, and it's going east. Then I have my y component, which is 964.2 kilometers north, and I've now drawn a new right triangle, and I need to find the resultant of that right triangle, and I need to find the angle. So I'd use Pythagorean theorem. I would carry all my numbers down, square, take my square root, and find my actual resultant. I think I have, yeah, I did something funky with this number here. So originally, I'm not sure how, yeah, I don't know if that 1.57 is right, but as long as you put the 964.2 over the 6,149.1 and you use your inverse tangent, then you should come up with the right angle. So yeah, just FYI. I think I messed up my PowerPoint and I can't go back and fix that, so that's why I colored that out. So my final answer would be 6,224.14 kilometers at an 8.91 degree north of east angle. So again, displacement has to have magnitude and direction. All right, so the riverboat problem, we're actually going to wait and talk about this when I'm in class, so we will do that on the back of your packet when I get back underneath your answers in the very back part. So we'll do our graphicals and this part when I get back. And now you could start working on some of your homework, and I recommend that you start with number 4. Okay? You guys have a great day.